we are rocket propulsion people. My co-founder and I and our core engineers. I think our core tech is like a refrigeration cycle. But the farther out into orbit you get, the longer the delays on communication are with your vehicle. So particularly if you're trying to rendezvous with something, like you can't have a multi-second delay.
Like it's required to be like felt relatively
You have to be autonomous. You have to. I mean, there's really no option around that. And so I think it is absolutely going to be like a key part of this vehicle that it has to be almost like fully autonomous to be able to respond to incidents and be able to course correct and track. We're going to need onboard compute. Which is another big problem that the space industry is trying to solve right now. The farther out you go, more radiation you have, so you have to radiation harden all these different components. Just builds the whole space economy, right, around everything there. But yeah, the reason I focus in is just we just started out and we're really kind of focusing on the core tech right now.
Ben, thanks a lot for joining me.
Yeah, absolutely.
Perhaps let's start out with you telling us about what Orbital Operations does.
Yeah, so Orbital Operations is developing a high-thrust space vehicle that'll be stationed out in orbit for military and logistics missions.
I guess let's perhaps first, like, what's your background? What brought you to work?
Yeah. So started off my career at Marshall Space Flight Center, so NASA, working fluid systems and rocket engine development. Then went over to SpaceX for a time. I was working on Dragon capsule. And then I was an early employee over at Relativity Space. So number 3 on the propulsion team there. I worked valves and actuators, instrumentation, fluid systems. Went over and actually owned the heat exchanger, did some turbo machinery stuff, and was actually a manager on the integrated design and analysis team before founding this.
Okay, and let's like talk about like maybe set the stage about like what the actual problem space is here. There's I guess first like, you know, it may not be intuitive to everybody that things move around as much as they do or don't in space. And so what are the, you know, why do things need to move around, and like what are the current approaches and what are the constraints? Yeah.
So I think the biggest thing, if we kind of like take a step back on like what satellites do, right, or what they have been developed to do up till now, has really been to not move, right? It's been to like go to a spot and station keep. And so
they do move, just not relative to
their orbit. Yeah,
they're doing one
and everything
specific movement over.
Yeah. And so, you know, they really weren't designed to change their orbits, probably a better way to put it. They were designed to station keep and stay in that location. It's been kind of a relatively new problem statement to say, okay, it needs to be able to avoid, you know, maybe started off more with like collision avoidance or, you know, the ability to kind of make sure it can't be, you know, directly looked at or messed with. And that's just been kind of building as, you know, the space becomes a little bit more adversarial and we start expanding out more. There is a dramatic need to be able to have something in space that has a lot more movement, because right now we're really restricted by the amount of propellant that you have and the types of propellants that you can use and store out in space for a long time, right? Like some of these geosynchronous satellites have to be out there for 15 years. And so station keeping propellant stored and using that is a huge restriction, particularly in an adversarial setting.
And people are trying to do something that's like not like, what is the state of the art?
Yeah, so state of the art right now, I would say propellant wise is hydrazine. That's really what a lot of these satellites have been using. And I kind of have to break off into like some metrics, right? So for, you know, rocket propulsion and satellite propulsion and like in-space propulsion, we use a term called ISP, which relatably is really just miles per gallon, right? So if you directly relate it to a car, it's just how much bang you get for your buck. And that puts you around, you know, maybe like 250 ISP. And so that paired with the way we do the propulsion and the thrust that we get, you know, maybe 50 pounds of thrust would be a high thrust system, maybe up to 100 pounds of thrust. And that's really like a pressure fed system where you just pressurize the tanks and it kind of blows down. You know, that's the state of the art. And obviously
like the basic physics of like displacement.
Yeah, and that's really like
push something one direction that pushes you the other direction.
Exactly. And rocket propulsion, this gets relevant with orbital operations and our choice in propellant, but you can really break rocket propulsion down. I like to break it down as like kinetic energy, just mass 1/2 times mass times velocity squared. So the mass and velocity are really your only two terms there for rocket propulsion. And so if you have a higher mass, it may go up a little bit, but if you have a higher velocity of the gas going out, it really gets you more. So a lot of times you're trading a lighter particle that you can go faster with because the velocity is squared. And so it really gives you more thrust.
Okay. So you want to shoot the heaviest thing out you can as fast as you can, but you want to weigh towards fast because it's squared.
Exactly. And so what that normally winds up meaning is you want the lightest molecule because you can get that going faster, right? Usually you're kind of inversely trading those, but one is squared. So you always want it.
Yeah. I guess it's some intuition about the discrepancy between the lowest and highest atomic weight is kind of interesting.
Yeah.
But
yes, yeah, it's
and like what the breadth is.
Probably oversimplifying things, but trying to keep it clear.
Okay, and also, but also the propellant weight is related to how much you can send up and how much it costs to send up. Is that part of the equation?
Yeah, I think there's two things. One is what you're talking about on how much propellant you're sending up and how much bang you're getting for your buck of that propellant. The other one is the form factor, right? Because movement hasn't been a big goal of satellites, right? Like changing orbits hasn't been a big goal of satellites. Recently, it's become more of a hot topic, which is a good thing for orbital operations. But it's basically you were trying to build your satellite with the least amount of propellant, right? If you could get away with a lower amount of propellant but still be able to station keep, that was a good thing. Rockets, it's very different, right? You almost want to boast about how much propellant you're able to do in comparison to dry mass, right? Because you're almost bragging, saying hey, I got away with as little structural mass as possible, and it's all propellant. And so it's just a very different dynamic, especially from where I come from on satellite versus rockets.
And then in the molecule you're booking, there's also how much you can store for how long and what density. Because if you start to think about moving around more, that's not always a one-time thing.
Correct. Yeah. I mean, the more you're moving around and expending that propellant, the less you're going to have at the end of life, right? So.
And then, all right. So from a use case perspective, what is immediately what is currently at the threshold of things that people want to do in space but are not, and is there a hierarchy of what is most important to move around soonest? Or
so we Orbital Operations is definitely looking to serve some of the problem statements that the U.S. Space Force is running into, for sure. That seems to be a very high priority. Movement is always a challenge, just like expending that propellant, the limited reserves that you have. The goal is really to make that not a problem, right? And so, when they talk about potential reconnaissance missions, or they talk, deterrence missions, or going out to cislunar, they are, the first point that comes up is how much range do you have? We use a term called delta V because, again, we're always moving. So range gets a little weird when you say I moved a mile, but you're orbiting Earth, so you're always moving. So you say delta V, it's just range. And it's always a key factor. If I'm going to go and try and take a photo of a satellite or do some reconnaissance, I'm going to burn this much propellant. It's always the first point they bring up. And if they move away and make it so you don't take a photo, how challenging it can be there.
Yeah. Okay. And then, so what led you to an intuition you could do much better?
Yeah, I think, we had a long kind of winding path for orbital operations. We were kind of looking into nuclear propulsion first and some of the advantages there. Really challenging, that I'm not going to get into because even more challenging than what we're looking to do, and some material science breakthroughs we'd have to do there. But we realized pretty quickly, even with nuclear propulsion, it's still all about sending a particle out the back as fast as possible. So the best would have been hydrogen, right? Liquid hydrogen, you heat that up, you shoot that out the back end, you have the tiniest molecule going out the back end as fast as possible. We immediately pivoted away from liquid hydrogen because we're doing a nuclear rocket engine and storing cryogenic propellants out in orbit. And I'll get more into storing cryogenic propellants because that's really the key of orbital operations. And we switched to a storable propellant, cuts the efficiency in half, which brings you right back to what we're using in the launch industry right now. My background, my co-founder's background, our engineer's background, which is, a propulsion system that's already really well known, right? Almost a heritage level propulsion system. I've done 2 rocket engine development programs. My co-founder's done 3. We know how to build rocket engines that aren't nuclear. And so we kind of pivoted over to, hey, if we just did cryogenic propellant storage, right? We could store these cryogenic propellants with a standard rocket engine. We were going to get to what we were doing with the nuclear engine with storables anyways, but we think this is a much better product because truthfully, we know how to make a rocket engine, right? That knowledge is out there. And what do we need to do to be able to store cryogenic propellants, which really is an advanced, in the simplest terms, an advanced refrigeration cycle. That's really what this is when you break it down. Very challenging high-speed compressors, gas-to-gas heat exchangers, turbo alternators. You're really trying to get your coolant, which is separate from your propellant. It's really just helium, because helium's the only thing that gets colder than liquid hydrogen, and it's still a gas. But you use that to chill your tanks down and make it so that you can store these propellants. Because otherwise, if you have these really cold liquids in a tank, and you put that tank out into orbit, and it's getting hit with sunlight and radiation and all these other effects, it would actually start to boil. And in order to have those tanks not pop, you have to vent the tanks. So cryogenic propellants are known in the industry as just not being storable. You couldn't have them for more than 2 or 3 days, right? But if you put this active chiller system on, you absolutely can, right? You can wick the heat away from the sun before it ever hits the propellants and keep them cold and storable and actually use them. And now you get the super high efficiency, you get very high thrust with technology propulsion that's already been developed.
Okay, and in modern rocket engines, terrestrial, I guess I don't know if that's right.
Yeah, launch vehicles
they're cryogenic hydrogen.
Yes, some of these cryogenic methane, some of them the upper stages, the ones that need efficiency, really go liquid hydrogen. So it's interesting now. Some of the new rockets being developed, like Stoke Space or Blue Origin, they use liquid oxygen and liquid methane for the first stage, and liquid hydrogen, liquid oxygen for the second stage, which is fine for a rocket mission because it's like a couple minutes long, right? Like you really only need your propellants long enough. And so a little bit of boil off in that time frame is okay. But it's not if you're trying to stay out in orbit for 10 years.
And is there anything different happening physically in those stages? Is it the same thing? Like does it interact differently with atmosphere? Is that
why they have the split?
Yeah.
Usually I think the easiest way to break it down on a launch vehicle side is that thrust is king for getting off of the Earth. Efficiency is king out in space. Now, we might take that to the other side where if you have no thrust in space or very, very little thrust, then these rapid movements also can't happen. But I think it's still core that, efficiency is king in space. And so on a launch vehicle side, if thrust matters the most, methane's a little bit cheaper. Volumetrically, it's condensed down a bit more. So there's a lot of trades you see with Starship as well as methane. So there's a logic to be had on just making a high thrust, lower efficiency engine on the first stage, but a higher efficiency engine on the second stage with liquid hydrogen, liquid oxygen.
And is there anything else that works differently about a rocket engine in zero atmosphere versus some atmosphere?
Yeah, it's definitely going to expand more as it goes out the nozzle, right? You don't have the pressure outside, basically squeezing your exhaust gas. So it will want to expand more. So those nozzles really get a lot larger. You can take advantage of that and really get more, thrust and efficiency out of your engines out in orbit. That's really the key difference that's going on there in comparison to, what the state of the art is for satellites right now, like hydrazine. They really don't kind of maximize on a rocket engine nozzle side and high thrust applications. That just really hasn't been the problem statement before, right? I think in the launch industry side, there's always been a focus on really maximizing that efficiency with these propellants. But yeah.
And I don't know, this is a dumb question, but in space, you're you're oxidizing and lighting on fire in the same way. Does it look the same?
Yeah, it's an interesting question. Now on the hydrogen oxygen side, when you burn it, it's pretty much clear. So it will look a little bit different. There is no interaction with the oxygen, but even here on Earth, there's times where if you have a hydrogen fire, you have to be very careful because you can't see it, right? It's a clear thing. you're always checking like FLIR cameras or, the joke in the like very old days when they were first working with hydrogen for like Saturn V program is like when they approached the test stand, they would walk with like a broom in front of them to see if it would like just catch on fire in front of them and be like, oh, okay. Yeah, there's still hydrogen fire there, before FLIR cameras and thermal cameras. But it's gonna look almost clear, maybe like a little bit of like a bluish hue, kind of just radiating off of the gas part.
And it like shoots out the nozzle at some rate,
Yep.
and then lights fire and then moves faster.
Yeah, so you're with a rocket engine, and the way we're doing it as well with pump fed engines, which is really for cryogenic propellants and launch vehicles, is the standard way to do it. You're pumping your liquid hydrogen and liquid oxygen into a chamber, and you almost have this shower head looking thing we call an injector, and that basically just mixes the two together, and you're combusting in that chamber. So you're reacting with both of them. It's burning, generating a ton of heat, which then ejects through a nozzle. And as you hit Mach 1 and then you go and expand the nozzle, it actually goes even faster as it expands out through that. It's always funny with, when I talk hydrogen and oxygen, because the byproduct really is water in the end. As you burn hydrogen and oxygen together, it's just H2O. That's what you're really producing.
All right, now we're through the basics of combustion engines.
Let's get a whiteboard. I'm down to draw it all out.
But then all of that, you're going and lighting the hydrogen and oxygen on firing space. But the hard part is refrigeration.
Yes, that's definitely like storing those propellants out in orbit. That's definitely the kind of core tech that we're really working on that enables us. The rocket engine side, like I think it's part of orbital operations mentality of like, we have this really high efficiency, high thrust propulsion methods. The refrigeration cycle unlocks that for out in orbit so that we can basically have the third stage of a rocket that's stationed out in orbit.
And then what's hard about, I guess, what is the state of the art of refrigerant on Earth? So I guess intuitively I'm it's hotter when you're in direct sunlight than you would be on the surface of the Earth. And then, and now you're under some power constraint where it had you need an efficiency that keeps things cold at the amount of sunlight that it's currently getting.
And always a weight constraint, right? Like you always want everything as small as possible. And I think this is an interesting thing as well on this cryo management system is it's one of the few kind of propulsion methodologies that actually scales better as your vehicle gets larger, because we cool the outsides of the tank. So as the tanks get larger, the surface area to volume ratio. Yeah. And so that's not normal for in-space propulsion. If you look at electric propulsion or pressure-fed systems, they don't scale up very well. We actually don't scale down very well. And so we want to be in that kind of larger category. State of the art, the challenge, it's really interesting because, on Earth, yes, we don't have the direct radiation and sunlight, but we also have air, which can be just hot ambient air, right? So if you're out in Florida or something like that, that's a challenging problem to handle. But then you can also use the air to your advantage, and you can use water, and you can use ground systems, and you can pull the heat away from your propellants and basically dump it. I'm talking about heat, you can just flow it at wherever you want, but you can basically dump it into water with standard radiators. This is what cars do, right? They have their water radiator systems. In space, we don't have any air. We don't have any convection. We definitely don't have the weight or the ground systems to have a water system. Even if we did, we couldn't flow air across it and just dump it to the air. So we have to use a closed loop system where we are basically compressing helium, and you compress it and it kind of heats up, and then you move it over and you have to radiate it away, which is basically the type of heat you see when something glows red hot. That's just pure radiation. So we have to radiate the heat away. And then we go through, a series of heat exchangers and then a turbo expander, which is just a really fancy way of we're just removing work from the gas, and it chills down to very low temperatures. We flow that on the outside of the tanks, which is where it interacts with the sunlight, basically wicks the sunlight away, which is direct radiation, and closed loop just starts all over again, goes back to...
because you're already in space, there's not if you're not in sunlight,
it's very cold.
There's no reason.
Yeah,
it stays cold on its own.
Yeah, and
there's no ongoing need to keep it cold. There's only a defensive thing against.
If you're on Earth, even if it's nighttime, right, you still have ambient air. Yeah. And so if you're in if there was a perfect world, we could just like hide behind an asteroid or something from sunlight, then yeah, sure, we wouldn't actually have to chill. It actually is cold enough to just have liquid hydrogen out there. But, you'll see a lot more as well with some of these like in-space compute companies as well, where they're generating heat out in orbit. Now, big talk is like the radiators. Like, how do you radiate away this heat without having air to dump it to? And so that we're in the similar category where we're really a thermal management problem.
Yeah, which is interesting because it's like, you mental model of refrigerators that it cools the things inside, but this is actually like a defensive layer against something that may, I guess, be on any side. I guess you might not kind of know what side of the satellite is going to be hit by sun.
Yeah, it all comes down to GNC and guidance and navigation. I mean, if we station ourselves in low Earth orbit, we orbit the Earth 16 times a day, right? So that's 16 sunrises, 16 sunsets, right? We're just like actively passing it. How are you rotating yourself or trying to hide it away? It's actually a very challenging kind of dynamics problem there. Yeah. And then as you go farther out, geosynchronous or lunar orbit, like you're not getting half of your time behind the Earth anymore. You are in direct sunlight and it's hard to avoid it. So the way we're really designing it is, we have to be able to remove sunlight as if we're just getting broadsided with sunlight pretty much all of the time. Because, there will be statements when we're out in geosynchronous or lunar and we are getting hit with sunlight constantly.
And then do you have to draw power off the satellite's like larger solar array, or do you like have to or do you have to factor that in for yourselves?
Yeah, we definitely will have solar power on our units. It's an interesting problem because our whole statement is like we are designing to move out in orbit, right? Like that's a fundamentally different product than I think what you see with a lot of satellites. Mm-hmm. And so being able to move, like a high thrust satellite might be 100 pounds of thrust. Okay, we're 15,000 pounds of thrust. We're mostly propellant. We're trying to be a lot of propellant. We look a lot more like a rocket. If we can't have flimsy solar panel basically, displayed out to the side, which is what you see in a lot of satellites because they don't move that much. If we try to move with a flimsy solar panel array with 15,000 pounds of thrust, those solar panels are gone. So like now we have to body mount them or figure out how to have them be deployable and retractable, right? Like it is a little bit of a different problem statement. We still need the power. Absolutely. You've got to run the compressor systems. You have to be able to run communications, any payloads that you have on board. But yeah.
And then how does this fit into how people build satellites? Do you have to operate, like how do you operate as a satellite engine company without being like a bus?
Yeah. So for us, we have the kind of like more reconnaissance, like military type of statement. And that really would be us like integrating like camera systems or communications, or even, as we get farther down the line, let's say you can do reconnaissance out in orbit and there's an adversarial satellite coming towards yours. What is the next step? You want to be able to deter, but you don't want to blow anything up in orbit. Let's be clear. Nobody wants that. You don't want shrapnel. So the kind of buzzword being used is like degradation technologies, high power microwaves. I say direct energy, not in the terms of like we're going to melt things out in orbit, but maybe you could damage a camera system on an adversarial satellite or something like that. That's what we would host on our vehicle on kind of the military side. On the logistics side, and what we've seen on kind of the commercial traction side has been actually allowing customers who want to go farther out to be dropped off in low Earth orbit. And then we would basically rendezvous with them, grab that satellite and ferry them out to higher orbits. So, take somebody out to geosynchronous orbit like Astranus, or, Astroforward wants to go to and mine asteroids, like got to go beyond the moon. And being able to take advantage of like Starship, which is really good at getting to low Earth orbit, but not good at getting out to higher orbits, or even maybe like Stoke Space, reusable second stages. Any company really that's like attacking the low Earth constellation market. we can let those customers take the cheaper rides to low Earth orbit and then give them an efficient ride out to the higher orbits. Cost and timeline breakdown, it's significantly cheaper on both.
Okay, so your form factor is like your own satellites that then move around others.
Yes, yeah, we are basically, we are stationed out in orbit, and we're either doing military missions or we're a ferry. Is where pretty much all of our commercial traction has come from.
How do you think about mission life when you're?
Yeah, so this gets into kind of like the not phase 2, because we're going to have to get into it pretty quickly, and there's a lot of interest in this. But you're going to have to get into refueling, right? So with this high efficiency propellant, this high thrust propellant, we have enough range to grab something in low Earth orbit, drop it off in geosynchronous, and then actually come back to low Earth orbit without a payload. And we chose liquid hydrogen, liquid oxygen, because it's the smallest molecule, highest efficiency. You can scale it with thrust, like all those benefits on the rocket propulsion side. Where the byproduct is water, you can actually get the other side effect where you can refuel with water. And they do this on the International Space Station right now. When I worked at Marshall, I learned a lot about this as well. When they want to replenish oxygen on the station, they actually launch water up instead of gaseous oxygen, and then they run it through electrolysis. You just have anode, cathode. It just breaks it up, hydrogen gas, oxygen gas. They actually dump the hydrogen overboard, and then they keep the oxygen for breathing. So for us, we have liquid hydrogen, liquid oxygen, so we can launch water. And now I don't need a cryo management system on my refuel tank. I need one tank, and water it's not down to those ultra low temperatures. I can actually do a bladder system. I can't do that in a cryo tank, right? Because once you're out in orbit, everything's just floating around. You can't have a bladder system when something's at 20 Kelvin. You don't have flexible materials that you could, press and squeeze. But with water, you can. And so you do that, you run it through water electrolysis, you get hydrogen gas and oxygen gas, and those basically trickle into your tanks, and you condense it down over time. So the trade-off, the downside of this is that it's going to take some time. Like a refuel could take a month to 2 months almost. I always tell people that if we get to a point on the commercial side where a month on a refuel is just so long because we have such a backlog of missions, we're in a good spot. We'll figure that out. We'll launch another vehicle up. We'll get more power up there to make the refuels go faster. But I think the advantages of being to refuel with water are huge. And then there's maybe even the third stage where everybody always talks that one of the first things. Well, maybe Astroforge will change this. They'll get their rare earth minerals. But the other side is mining water, right? Water from asteroids or water from the moon. And they always talk about you can make rocket propellants. I don't know who's buying those, but we all buy those now. Like if you can get water off the moon, I'll buy that. So that's a little bit farther out, but definitely an end state for us.
Do you have to warm it up to?
Yes. Yeah. You're actually in the opposite state because it's ice. A lot easier to put some heaters and not quite the temperature extremes. But
yes, in the sun for a little while.
It's all thermal management problems, and we're gonna get really good on thermal management.
Cycling one way. Have there been points? Are there moments where you're like worried? Like this is not has this just been like? We understand how to do this. It's just straightforward engineering. Do it step by step and get through it. Or were there walls where you're like, I'm not sure how this is going to be possible?
No, I think on the engineering side, definitely felt it a bit with the nuclear propulsion. But on what we're doing is not a science experiment in any way, right? Like it is an advanced refrigeration cycle where the challenge is engineering execution, not is this possible? Like it's demonstrated on the ground. The challenge is really like building it to go out into orbit and
you're able to just it's pencil out the tolerance for power going into amount of refrigeration.
We're going to have, like any space thing, it's probably going to take multiple shots. We're going to put multiple like subscale demos up and really kind of break down the engineering challenges. My background is all rocket engine development. My co-founder is the same. Our first founding engineer, like we know turbo machinery and heat exchangers and aerospace grade components. That side, I'm trying to not be a cocky engineer, but that side I'm like very confident in. The business side is very new to me and my co-founder. And so I think early on we had hints from the US Space Force and hints from commercial customers like, yes, this would be advantageous. And I think, as we went through like Y Combinator, they really helped us flush out a business plan and how to prove that out and how to really understand if there's true traction there. And I think the more we interacted and got more credibility and more conversations we had, it's only been building in confidence on like, this is absolutely something that we need. And quite frankly, like could have been done even a little while ago, I think. So I think we're confident on both sides.
The the mission complexity seems to grow quickly from where you're starting to like, let's refuel the thing with water. Like, how do you decide the points at which you send something into space? To validate out.
I think the first product, and this is a good alignment, I think, on some of the possible like military use cases, right, is the ability to be stationed out in orbit with a ton of range and a ton of thrust, and a first product that just has that and you're using it until end of life. Maybe you put a refuel port on it, but your kind of initial baseline is like, this isn't going to be refuelable, and that's okay. That's still an incredibly powerful product.
Yeah. There's nothing like it. So the cost constraints are not as high.
And if you get to that point, you've kind of bought down quite a bit of complexity. And so now you're going to the next bit of complexity where everybody wants to go in the market, right? Is refueling. Like that's been a common thread that has been kind of unraveling the last like 10 or even 15 years. So even though it does add a layer of complexity, there's a ton of support on like, can you make this thing refuelable? We're fine to get that initial product out the door and then kind of step into the next level of complexity.
It's like a lot of things in space, you assume the costs are gonna like come down over time, but it also, there's like this elegance where like there's a class of people, there's a subset of people with such an acute need that they will support the early, very expensive versions as you get to, and then you expand the market as you're able to make this cheaper.
Yeah, absolutely. And we fit into that category of making things cheaper, right? Like it's crazy because if you look back again, I worked at Marshall Space Flight Center, which was like the Saturn V like era, Warner von Braun, and the initial concepts they even had back in the 60s and 70s was like low Earth orbit is the train stop, right? Everything should be dropped off there. You're either returning back to Earth from there, or you have systems that just stay out and live in orbit. And that's kind of the next level. This like, if you hear some different talks at conferences from different retired generals and others, like we're entering this third age of like in-space mobility and logistics and refueling. And we're kind of at the spearhead of that with a couple other startups, right? So, hopefully we get to a point where it's like when we get operational and we're commercial, the cost of getting to geosynchronous or lunar orbit or medium Earth orbit, whatever it is, comes down as well. And so we're hopefully just building on that decrease in cost.
And then you mentioned astroforge, like, is this, when we think about things that beyond just orbit, right? Like, I guess, like how much is that part of the space economy limited by engines that move things around?
Yeah, just like in space mobility, I think a lot, right? I think the ability to go out to asteroids, if let's say we flush out all the complexity, right? Like, and we can make it cheaper and faster, and you get dropped off in low Earth orbit, and we take you out to the higher orbits, then yeah, it opens that up. I think it opens up deorbiting and cleaning up space, right? Like a huge limitation there is how much range and ability to move things around. I think if we get to a point of either mining on the moon or mining on the asteroids and bringing things back, I think you're making trade-offs, always making trade-offs. It's always top of mind of like, how much can you carry versus how much propellant do you have? That's like the number one thing that comes to mind for pretty much any space, architect. So hopefully that just opens up with this type of technology in this vehicle.
Yeah. Yeah, that's really interesting. There's like some relationship between thrust and like.
Yeah, it's all like
where you go, because it's like once you get up to speed, you keep going.
Yeah, it's all about,
you need to be slow down.
It's all about changing your velocity. That is really like space travel. And so if you're heavier, you need more energy or more thrust, whatever it is, your trade-off there, to change your velocity, right? If you're a really heavy thing and you're only pushing with 0.001 pounds of thrust and you only have so much propellant, you're not going to change your velocity very much. Whereas if you open that up, your high efficiency, high thrust, you really open up your possibilities.
Yeah, that's really interesting. How much do you guys, I mean, you guys like, is there a lot of, I guess I just asked this to everybody, so I'm still kind of curious. Like, I imagine there's some amount of software relevant to this.
Oh yeah, there is a lot, and we're going to have to dig into this quite a bit more in the future because we are rocket propulsion people. My co-founder and I are core engineers. I think our core tech is like a refrigeration cycle, but the farther out into orbit you get, the longer the delays on communication are with your vehicle. So particularly if you're trying to rendezvous with something, like you can't have a multi-second delay.
Like it's required to be like relatively
to be autonomous. You have to. I mean, there's really no option around that. And so I think we're very focused right now on like the core tech of like, we're going to solve the movement problem, but like it is absolutely going to be like a key part of this vehicle that it has to be almost like fully autonomous to be able to respond to incidents and be able to course correct and track. We're going to need onboard compute, which is another big problem that the space industry is trying to solve right now. The farther out you go, more radiation you have. So you have to radiation harden all these different components. Just builds the whole space economy, right, around everything there. But yeah, the reason I focus in is just we just started out and we're really kind of focusing on the core tech right now.
Is anything, I mean, is the current generation of AI useful at all? And any of this, like the code you're writing or like
it is. It's
research
just useful. Yeah. I think, if you get into really complex, like orbital maneuver calculations, you get maybe a little bit limited, but it is crazy because I will go through my entire workbook and be like, and we calculate range with delta V. So I'll be like, okay, this is how much delta V I think we have based on all the mass we have. And like, here's what it takes to go from low Earth orbit at a 28-degree inclination out to direct inserted into geosynchronous and all that stuff. And I'm like, I really hope that's right. And I go to ChatGPT and just, hey, can you calculate that? Just give it the bare bones and see if it comes up with the same answer. And it's like spot on, same answer. And you're like, wow, that's great. Show me how you got there, and then spot check my work. And I was impressed because that's not an easy calculation.
The Math Olympiad is actually in your it overlaps with the kind of problems you need to figure out.
I think more tools on the AI side are really going to help on the potential for like CAD and CFD as well. I think that's, beyond just kind of the like standard calculations on workbooks and things. Like we're doing a lot of like advanced 3D printed heat exchangers, which really hard to do traditional CAD models with. So you have to do very specialized CAD models that are coming out, and then trying to do like fluids analysis and simulation with these really complex models, like very challenging. But, I think AI is also supporting in that realm as well. So very excited to like see how those tools continue flushing out. And then, AI out in orbit is 100% going to be needed. So it's going to be interesting.
Awesome. All right. Well, this has been really, really fascinating. I really appreciate the way you're able to explain these things. So thanks a lot for coming by.
Absolutely. Thank you for having me.